So good morning, everybody. I hope you've had a lovely week so far and that your odd period classes went well and that you had a good weekend. All those things. I know it's weird to say I hope you had a good weekend on Thursday, but you know, I haven't seen you since last week. So welcome back. Today we're going to be doing our lesson on section 8.3, which is estimating a population mean. This is incredibly closely related to what we did last week with the population proportions. We just essentially need to change a little bit of the notation and add some other conditions, and we do basically all the same math. So we have our lesson for today. I will encourage you to take some notes, although a lot of the presentation that we have is just kind of like justifying the rules that we'll need to write down and be able to use. So I'll kind of say when it's something that I think you need to really have in your notes because you need to be able to use it. So we'll go with that. We're going to start here. So I'm going to do my thingies. Oops. I clicked something before I needed to click it. There we go. Let's do this one. Yeah, there we go. Boom. Okie dokie, so here we go. Chapter 8, Estimating with Confidence, Section 8.3, Estimating a Population Mean. And this is where we're going today. So our objectives today, we want to be able to state and check the random 10% normal large sample conditions for constructing a confidence interval for population mean. Just like with population proportions, we had a set of conditions, right? Random 10% and large counts that we had to check before we could construct our interval. Same idea applies here. We need to be able to explain how the t-distributions are different from the standard normal distribution and why it is necessary to use a t-distribution when calculating a confidence interval for population mean. When calculating intervals for means, we cannot use table A. We use what's called table B, and it's the t-distributions. We'll get to that today. We need to be able to determine critical values for calculating a C% confidence interval for a population mean using a table B, or technology. We can use our calculator to find these. We need to be able to construct and interpret a confidence interval for a population mean and determine the sample size required to obtain a C% confidence interval for a population mean with a specified margin of error. So it's a lot of the same things we already did for population proportions. We're now going to shift and apply these things to means. So the first thing we start with is kind of our justification for the t-distributions in table B. Right, when sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing. And this is what we've done previously. We find the z-score for the sampling distribution by taking x bar minus mu divided by sigma divided by the square root of n. This is implying we know the mean and we know sigma. And this is what we've done. We start with our sampling distribution, we standardize, and we get our standard normal curve, and allows us to do normal calculations. When we don't know sigma, we can estimate it using the sample standard deviation S sub x. However, what happens when we standardize and we're not using sigma? We're using the sample standard deviation. Right? That gets us to the new distribution, a t-distribution. And this has a different shape than the standard normal curve. However, it is still symmetric with a single peak at 0, but it has more area in the tails. It's more spread out. So this is a comparison of the two, right? The t standardization, so to say, and the z-score. We notice that t is way more spread out. It's a little shorter, not as tall, way more spread out, a lot more data in the tails. Our standardized z-score, a lot taller, way less variation. This is a major difference between the two, between the standardized score that needs sigma to work and our t distribution. Like any standardized statistic, t tells us how far x bar is from the mean in standard deviation units. It's just using t instead of z. There is a different t distribution for each sample size specified by its degrees of freedom. We'll explain what a degree of freedom here is in just a moment. Would anyone like a moment to write anything down? So when we perform inference about population mean using sigma, population mean mu, using a t distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size n, making df, which is just the notation for degree of freedom, equaling n minus 1. Right, we'll write the t distribution with n minus 1 degrees of freedom as t sub n minus 1. This should say mean. I'm not sure why they have the same proportion. So we have conditions here. Draw an SRS of size n from a large population that has a normal distribution with mean, mu, and standard deviation sigma. The statistic t equals x bar minus mu divided by the standard deviation of the sample divided by the square root of n has the t distribution with degrees of freedom df equals n minus 1. When the population distribution isn't normal, the statistic will have approximately a t n minus 1 distribution if the sample size is large enough. This gets closer, we'll have a list of actual conditions. This is one concept of that. The degrees of freedom, essentially we use n minus 1 to be conservative, to make sure we're not overestimating. This comes into play later. I don't believe it's important that you write this yellow box of information down. When comparing the density curves of standard normal distribution and t distribution, several facts are apparent. First, we have the density curves of the t distributions are similar in shape to the standard normal curve, and that's what we see here in the image. Right. Our normal curve is this line here that's the tallest curve, but also the narrowest curve. The spread of the t distribution is a bit greater than that of the standard normal distribution. Right. And we get these varied t distribution curves because the variance of these curves depends on the size of the sample. This relates back to what we learned in the previous chapter, that larger sample sizes create less variance, makes our distribution more narrow. Smaller sample sizes create a more spread distribution. So the wider, like this dashed curve, the wider and shorter curve goes with 2 degrees of freedom, implying a small sample size of 3, n equals 3. And then we get a little bit more narrow, a little bit taller distribution when we go to 9 degrees of freedom, or a sample size of 10. Distributions have more probability in the tails and less in the center than does the standard normal. We can see that in the image. As the degrees of freedom increase, the t density curve approaches the standard normal curve ever more closely. And again, that's related to a larger sample size being more accurate and getting us more closer to normal. And we saw that behavior in the previous chapter. As we get larger and larger sample sizes, as long as we still stay within our 10% condition, things tend to turn normal when we're looking at our sampling distributions. So we're now going to see an example of using our t distribution and table B, getting a critical value t star. So just like with our proportions, we used z star as the critical value from table A. T star is the critical value that we get from table B. So what critical value T star from table B should be used in constructing a confidence interval for the population mean in each of the following settings? So first we'll look at a 95% confidence interval based on an SRS of size n equals 12. In table B, we consult the row corresponding to DF equaling 12 minus 1 equals 11. This is a little section of table B. So we have a row header here called, or a column header here, DF. We find 11 down that column. We move across that row to the entry that is directly above 95% confidence level on the bottom of the chart. The bottom of table B is a list of confidence levels going from 50% to 99%. I think 99.989. Anyhow, we find that intersection, we get 2.201. So the desired critical value is T star equaling 2.201. So let's look at the full table B here real quick. I need to erase that. I thought I did. Let's see. All right, so this is table B. This is the version of table B you will get on the AP exam in your things that you're allowed to use. Notice here we have our degree of freedom column. We have our confidence level that goes from 50% to 99.9%. And all the things inside here are critical values for T star based on your degree of freedom and confidence level that you want. We are not right now really using the tail probabilities, so we're not really considering this top row yet. So that's what the full table B looks like, because our example only shows a section of it. Look at another example where we're doing a 90% confidence interval from a random sample of 48 observations. This is going to work a little differently. With 48 observations, we want to find the T star critical value for DF, degrees of freedom, equaling 48 minus 1, which is 47, and a 90% confidence. We do not have 47 on the table. Right? There is no DF equaling 47 row in table B. It's not because we just chose not to list it, it just isn't on table B, it's not part of it. So we use the more conservative degree of freedom equaling 40. Right? We err on the side of being conservative instead of overestimating. Right? Even though 47 is closer to 50, we go back down to 40 to be conservative. That's just the rule. We play by Price is Right rules. You want to be as close to the degree of freedom as possible, but you're not allowed to go over. So the largest value that's not greater than 47 is 40, so we use that. And so then we get a corresponding critical value of T star equaling 1.684. And we'll use that as our critical value in our calculation. Is there anything I can clarify so far? Okay. Now here's our full list of conditions for constructing a confidence interval about a mean. All right, we must check for randomness. The data comes from a well-designed random sample or randomized experiment. We need to check the 10% condition when sampling without replacement and check that n is sample size is less than or equal to 1/10 of the population size. Most of the time we will be sampling without replacement. So you usually have to check this condition. And then we have the normal/large sample. This has a few different things about it. If the population has a normal distribution, or the sample size is large, n being greater than or equal to 30, we're good to go. If the population distribution has unknown shape and n is less than 30, meaning our sample size is less than 30, we need to graph the sample data and assess the normality of this. Got to make a dot plot box plot, histogram, something so you can see the shape. And we cannot use T procedures, meaning we can't use table B if the graph shows strong skewness or outliers. If this scenario comes up where you have to graph your sample data, or you're provided with a graph of sample data, it will be very apparent that it is either strongly skewed or there's outliers. It will not be a judgment call. It's not going to be like, well, it's kind of skewed or a little skewed, so maybe, maybe not. It's going to be like severe so that it's not a question. Or they will tell you that the graph just doesn't have skewness or outliers just in part of the question setup, and you can just assume that it's okay. Right, but these are our conditions we must check, and we must show that we've checked them when we solve problems. I'll demonstrate this later. Does anyone need a moment to write any of this down? When the conditions for inference are satisfied, meaning those three things we just saw on the previous page, the sampling distribution for X bar has roughly a normal distribution. Because we don't know sigma, we estimate it by the sample standard deviation S sub X. Right? The standard error of the sample mean X bar is S sub X divided by square root of N, where S sub X is the sample standard deviation. It describes how far X bar will be from mu on average in repeated SRSs of size N. All right, so just like with population proportions, we had a standard error, right? And that was the square root of p hat times 1 minus p hat divided by n. Gave us our standard error. This is the similar thing that we use for means. This is our standard error. To construct a confidence interval for mu, we replace the standard deviation of X bar by its standard error in the formula for the one sample Z interval for population mean. Use critical values from the T distribution with n minus 1 degrees of freedom in place of the Z critical values. And we get this, the same format that we used for proportions, statistic plus or minus critical value times standard deviation of statistic, and we replace all the things. The statistic we're using is X bar, the critical value is T star, and the standard deviation of the statistic is replaced with the standard error, which is S sub X divided by square root of N. And that gives us our inference method, the one sample T interval for population mean. Right, and this is very similar to the reasoning for the population proportion. When conditions are met, a C% confidence interval for the unknown mean mu is X bar plus or minus T star times S sub X divided by square root of N, where T star is the critical value for the Tn minus 1 distribution with C% of its area between negative T star and T star. This you're going to want to put in your notes. This is a formula you need to be able to use and apply, just like the one that we did for proportions. Can you raise your hand if you need a moment to write this down? Okay, so let's see an example. So environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides, or NOx. Researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675, and the standard deviation was 0.3332. We want to construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. Whenever you see construct and interpret some confidence level for some mean or proportion or some other statistic, you need to go do the 4-step process: state, plan, do, conclude. This is the roadmap that helps make sure you cover all the things that you need to have when you answer problems on the AP exam. So first, we state we want to estimate the true mean amount mu of NOx emitted by all light-duty engines of this type at a 95% confidence level. Right, so we've stated the parameter, right, that we're interested in and the confidence level that we want. Plan. If the conditions are met, we should use a one sample t interval to estimate mu. Part of the plan is stating this and then checking your conditions. Random. The data came from a random sample of 40 engines from the population of all light-duty engines of this type, so we're good to go. It was a random sample. 10%. We are sampling without replacement, so we need to assume that there is at least 10 times 40 equaling 400 light-duty engines of this type. We get to make that assumption primarily because they didn't give us the size of the population, so we can't actually check that it is 10% or less. And since we've been asked to find this interval, we're going to assume that we can. If we were provided the actual population size to do the math and check to make sure that the percent works out, we need to show that. Large sample. Right, we don't know if the population distribution of NOx emissions is normal, but because the sample size is large, n equals 40, which is greater than 30, we should be safe in using a t-distribution. So we've now done the first two steps of our four-step process. We've stated what we're going to do. We've set out our plan and we've checked our conditions. Now we do math. From the information given, x bar is equal to 1.2675 grams per mile, and the standard deviation of our sample distribution is 0.3332 grams per mile. To find the critical value t star, we use the distribution with degrees of freedom 40 minus 1, which is 39. Again, there is no row corresponding to 39 degrees of freedom in table B. We can't pretend we have a larger sample size than we actually do, so we use the more conservative degrees of freedom equaling 30. And we find 95% along the bottom, and we get the intersection, we get 2.042. So we know our x bar, we know s sub x, we now have our critical value. The only thing left is to actually calculate the interval using our statistic plus or minus critical value times standard error. And that's what we set up here. So we get x bar plus or minus t star times the standard error equals 1.2675 plus or minus 2.042 times 0.3332 divided by square root of 40. We get 1.2675 plus or minus 0.1076, which gives us the interval 1.1599 to 1.3751. Right? You always want to list the smaller value first in the interval and the larger value second. It's a lower boundary to the upper boundary. Everything in between is considered a plausible value. Done our math, we can now write our conclusion, which is absolutely necessary. You must do the conclusion statement. Right? We are 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. And we're just using the sentence frame that we saw in 8.1. We are 95% confident that the interval from blank to blank, provide your unit of measure, this is grams per mile, captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. We just steal essentially the sentence, the end of the sentence that was in the question originally of construct and interpret a 95% confidence interval, blah, blah, blah. Right? We just complete this sentence with our values. Is there anything I can clarify on this example? All right. Then similarly to what we did with proportions, we can choose a sample size before we go and take our sample. And we have these things that we must consider. To determine the sample size n that will yield a level C confidence interval for a population mean with a specified margin of error, ME, we must first get a reasonable value for the population standard deviation sigma from an earlier or pilot study. Right? We have to have something to use as the standard deviation. It could be from a previous sample, like I said, earlier or pilot study. That's okay to use. It's the best we have. Unlike proportions, if I don't have something to use, I can't continue. There's no default value. Like with proportions, we can say, well, I don't have a previous study, so I'm just gonna use 0.5 as my estimate. We can't do that here. It's not allowed. Right? We have to have something to use. Then we find the critical value Z star. We're now back to table A from a standard normal curve for confidence level C. We set the expression for the margin of error to be less than or equal to ME and solve for N. Right, and that gives us Z star times sigma divided by square root of N less than or equal to ME. We rearrange this to solve for N. So we need a moment to write any of this down. So then here's our example on doing this part of the process. We have researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter, mg per dl, of the true value of mu at a 95% confidence level. Previous study involving this variety of monkey suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. All right, our problem here, obtaining monkeys, is time-consuming and expensive. So the researchers want to know the minimum number of monkeys that they will need to generate a satisfactory estimate. All right, so we're at a 95% confidence, and using table A, we get a Z star of 1.96. And we've seen this result previously from table A. We're going to use sigma equaling 5 as our best guess for the standard deviation of the monkey's cholesterol level, as that was what was provided from a previous study. And we set the expression for the margin of error to be at most 1 and solve for N. So we get our setup here, 1.96 times 5 divided by the square root of N is less than or equal to 1. We multiply each side by the square root of N. And we get 1.96 times 5 divided by 1 is less than or equal to the square root of N. We square both sides, and we get 96.04 is less than or equal to N, meaning N is greater than or equal to 96.04. Because 96 monkeys would give a slightly larger margin of error, because it violates our inequality, the researchers would need 97 monkeys to estimate the cholesterol levels to their satisfaction. Is there anything I can clarify? Okay. So then, that is the end of this presentation. However, I do have a couple of example problems that I'd like to do with you guys as well. A couple more, show you a couple more things on how to use this, hopefully to help it make a little more sense. So we're going to look at that. And here's our examples. So our first example here, right, is having to do with constructing and interpreting a confidence interval. Right, so we start by just reading our context. We have bone loss by nursing mothers. Breastfeeding mothers secrete calcium into their milk. Some of the calcium may come from their bones. Some mothers may lose bone mineral. Researchers measured the percent change in bone mineral content, BMC, of the spines of 47 randomly selected mothers. Right? The 47 randomly selected mothers is probably something we want to make note of. During 3 months of breastfeeding, the mean change in BMC was negative 3.587%. Right, and that's our mean. And the standard deviation was 2.506. Right? So this is what we get to start with here. We know that 47 here, that's the N, it's our sample size. Negative 3.587% is X bar. 2.506% is our S sub X. We're constructing and interpreting a 99% confidence interval to estimate the mean percent change in BMC in the population. Because we're being asked to construct and interpret, we use our 4-step process. Right? So we start by stating. Right? We want to estimate the true mean mu percent change in BMC in this population with 99% confidence. All right, so I've stated the parameter mu that I'm interested in and at what confidence I want it. Then we move to our planning phase. If conditions are met, we will use a 1 sample t distribution to estimate mu. Now, the only reason I can use mu in this sentence is because I said what mu is in the previous statement. If you did not use mu in the previous statement, you would just write the word mean here. Not a big difference, but it's an important one. So that means we now need to check our conditions. Right, random, 10%. And a large sample. All right, and the mothers were chosen randomly. So we're good. That's really all we have to say here. In the context, we were told that the 47 randomly selected mothers, right? That's all we need. Right? 10%. We can assume there are more than 47 times 10 equals 470. Nursing mothers. It's just a fair assumption to make, and they didn't give us any way to disprove that. And lastly, our large sample. Since n equals 47 is greater than 30, we can use the t distribution. Right? And so we're good to go. We've checked our conditions. We're done with the planning part. Now we have to do some math. Right, so we know x bar, that is negative 3.587%. We know S sub x, and that was 2.506%. We know n, right? And so our degree of freedom equals 47 minus 1, which is 46. Right? This value is what we'll find down this row of table B. And we want 99% confidence. So we know what to look for to get T star, which is the last value we need to do our calculation for the interval. Right, so we're gonna look at our table B here. Right, and so on table B, once again, 46 does not exist, right? We go from 40 to 50. We're going to use 40, right? Because again, that's as close as we can get to 46 without going over. Right? So we be cautious and we use that. Right? And then we're doing 99%. So we find that along the bottom here. We'll follow the 40 row across. We'll go up from 99%. And we get 2.704 as our T star value. Now we can find our interval. So we will now do our calculation. We have x bar, negative 3.587, plus or minus T star, 2.704, times S sub x, 2.506, divided by square root of 47. And this gives us the interval from negative 4.575 to negative 2.599. Right, so this is our interval. Does not go. Right, now we've done our calculations. We can go to our conclusion. And now we say we are 99% confident that the interval from negative 4.575 to negative 2.599%. Captures the true mean percent change in BMC for breastfeeding mothers. And that's our conclusion sentence. Is there anything that I can clarify from this example so far? I mean, it's very similar to what we did with proportions. And then our next question here, based on your interval from part A, do these data give good evidence that on the average nursing mothers lose bone mineral? Explain. All right. And so basically, the answer is yes. All right. So since all the plausible values are negative, implying bone loss, the data give convincing evidence that breastfeeding mothers lose bone mineral on average. All right. Now, the thing that we want to take note of here is in this response, we're giving a very clear explanation, and we're also being very specific to the context again. I'm not just saying this is plausible because all the values are negative. Right? We're giving a complete answer. Is there any questions? Anything I can clarify? All right. So we'll go to our last example here. We have the SAT. High school students who take the SAT math exam a second time generally score higher than on their first try. Past data suggests that the score increase has a standard deviation of about 50 points. We'll need that. How large a sample of high school students would be needed to estimate the mean change in SAT score within 2 points with 95% confidence? Right. So this is a question about sample size. So we're going to use our formula here with Z star times sigma divided by square root of n less than or equal to ME. Right. We know that Z star is going to be equal to 1.96 from our previous results at a 95% confidence level. That's the Z star. We're estimating sigma to be 50. Right? And that's because of that assumption that was given to us in the context. The margin of error is 2 points from here. And now we've used, this is all the data we have. Now we can solve for n. So we get 1.96 times 50 divided by square root of n. So less than or equal to 2. Right. We will multiply each side by the square root of n and divide each side by 2. Right, and that moves everything where we need it. Right? The square root of n is canceled on the left-hand side. The 2 gets canceled on the right-hand side. We are left with 1.96 times 50 divided by 2 is less than or equal to square root of n. Now we have to square both sides. The squaring cancels out the square root. And we end up with n being greater than or equal to 2,401. We've actually landed on a whole number, which is kind of nice. And so we can conclude we would need at least 2,401 high school students I'm missing some words here, sorry. In our sample to estimate the mean change in SAT score within 2 points with 95% confidence. Again, we do the math here, we get a solution, and then we kind of write a sentence to summarize it, tie it all together. Is there any questions about either of these two examples?
Why did you get 1.96?
So the 1.96 comes from the Z star, which is from table A, with a 95% confidence interval. So if we go back to table A, right, we have 95% confidence leaves 5% outside of the center, which gives us 2.5% on each tail. So we find 0.025 on table A on the interior, and that's going to be this right here. Right, 0.025 actually exists on table A, and that corresponds with negative 1.9, right, and 0.06. And so that gives us a z-score of negative 1.96, which then as a z-star, a critical value, we just use the positive and we have 1.96. And so we use that as the critical value. Yeah.
Thank you.
You're welcome. So anything else I can clarify? Any other questions? Okay. So here we go. So that is the lesson for today. Tomorrow we'll be doing some more practice with section 8.3. I also encourage you, please look at the practice problems and solutions that are available in the class resources. There's also, like, between estimating population proportions and population means, there's like 10 AP Daily videos. There's a lot of information, a lot of available resources here for these two sections. So I encourage you to take a look at those. I've also got the videos for the calculator instructions on how to use the calculator to get a population proportion interval, a population mean interval, and to actually get T star values. All right, those 3 videos are in the resources for sections 8.2 and 8.3. So I encourage you to check those out as well. Other than that, we will see you tomorrow to practice section 8.3. I hope you have a wonderful rest of your day. We'll see you soon. That's it.